Hello and welcome. In this video we will cover laser cutting. Laser cutting is the most widely used laser process that we have today. It is a process in which we have many years, decades of experience, and still it is today, even today, one of the most researched laser application topics that we have. And the content is structured in 4 divisions. We first will look at the basics of laser cutting, and then we will go through the 3 main areas of cutting in terms of their classical domains. One is laser sublimation cutting, one is laser fusion cutting, and the third one is laser oxygen cutting. The basics of laser beam cutting are rather simple. We focus the laser radiation onto the material. We increase the intensity such that the absorbed energy is leading to melting or vaporization of the material, and we take the material away in a molten or vaporized state, supported by inert or reactive gases. It is shown in the sketch on the right-hand side, where you can see the laser beam coming from the top, melting the material in parallel. Coaxially in a nozzle we apply a gas jet which accelerates the melt and helps the melt to get blown out of that processing zone, usually to the bottom of the cut. The advantages of these cutting processes compared with conventional processes are that we can have much higher processing speed, low heat load, little distortion, very precise cuts, and no oxidation of the cut if we use inert gases. And in most of the cases, post-processing is not required. If we look at the individual process parameters which influence the process, of course the laser plays a dominant role in terms of wavelengths, intensity, beam quality, beam diameter, polarization, and the laser power, of course, and the question how we apply it time-wise. CW, continuous wave, or pulsed. The cutting gas, of course, is important. It can be inert, it can be reactive. The material, actually there's no material that we cannot cut with a laser, and the handling needs high precision control, and then we sometimes need to orient the processing head according to the direction of cutting, especially if we work on higher gauges of materials. The optics also are very important in terms of focal length, focal position, and imaging properties. If you look at the process, imagine the laser coming in from the left, and here we have the material now. Then of course in the projection of the cutting curve, which is not indicated in this picture, we will have a changing intensity distribution depending on the position along the optical axis. This is indicated here by the so-called isophotes of the Gaussian beam. In this case we took a TM00 Gaussian beam, and you see that we have an isophote where the intensity is defined by half of the peak intensity, and this corresponds more or less rather exactly to the Rayleigh length of the Gaussian beam, and the Rayleigh length is, so to say, the focusing depth of the beam, and this usually is matched to the cutting thickness by 1:1, which means that we choose the focusing of the laser beam, and so to say the distribution of the isophote where the intensity drops to about 1/2 is corresponding to the Rayleigh length of the material, which is the dimension of the cut that we want to perform in terms of material thickness. We start with the first of the 3 cutting processes, laser sublimation cutting. As the name says, most of the material is vaporized and we have practically no melt formation. There may be a small melt film thickness if the material can melt. We have very smooth cutting edges. We have a low heat load, no oxidation, And we can apply this process very efficiently for materials who do not really have a distinct melting temperature that holds, for example, for wood, paper, ceramics, or plastics. You see some advantages here. The disadvantages are that we need relatively high intensities because we need to overcome the vaporization energy density. If we use laser cutting with melt, then we just need to go beyond the melting density. This is an example of a cut in wood. The thickness is about 2.5 centimeters, and you see a kilowatt CO2 laser is sufficient to cut that with about 1.5 meters per minute speed. As you can see, the surface looks quite not carbonized, and this is true, but not 100%. Actually, there is carbonization, of course, because we vaporize wood. And this carbonization is so thin that it is below about a micron, so the visible light does not resolve this carbonization film. The second process is laser fusion cutting. In fusion cutting, most of the energy is used to melt the material, and then it is ejected by an inert gas like nitrogen, argon, helium, or any other inert gas. The advantages are that the required energy is lower compared to sublimation. We get higher cutting speeds at the same intensities, and we have no oxidation of the cut. We can cut practically all materials which show a melting behavior, so that is true for thermoplastics, glass, and of course all metals. The disadvantages are that we have requirements for rather precise adjustment of all the process parameters. It has been shown over the decades of application that this is one of the most demanding parameters for long-term operation and application. That is the precision and the repeatability of the precision in the positioning of all the relevant components in a laser cutter. Liquid melt forms striations. So these striations, as we will learn, are very systematically. Then they can lead to dross, which we don't want, of course. And sometimes in these inert gas supported cutting processes we get pretty high consumption of cutting gas because we work with pressures up to 10 to 20 bars in the corresponding nozzles. Here you see a schematic drawing of how the cutting process works. We have the laser coming from the top, then we have some vessel pressure chamber in which we form a laser gas jet. This is pretty simple if we have transparent optics, if we use them. Then we get a coaxial cutting gas jet which expels the melt out of the cutting curve downward parallel to the optical axis. If we use reflective optics, the system is a little more demanding. As you can see here, this is a mirror system which we use. And the focused laser beam is here exiting this nozzle system, and the nozzle consists of a double cone coaxial nozzle which allows us again, even with mirror optics, to form a coaxial gas jet coaxial to the laser beam in order to collinearly supply the mechanical energy of the gas jet with the optical energy of the laser beam. As a result, we get cuts like this. The application here shows a 15 millimeter aluminum alloy cut, and what you see, it is very rectangular. It's very nice, way better than all other plasma cutting processes. However, we have a micro roughness formed by these striations, which already you can see have different zones in which they appear in different nature. In order to understand what is happening, these processes have been simulated quite extensively, and in this first video animation you can see what is happening. The laser radiation hits the cold part of the workpiece to be cut right here, and then of course it starts to form a melt film. This melt film is very thin in the beginning, so the surface tension exceeds the force that is needed to blow out the melt along that back of the cutting curve, so it will still stick here. However, if you allow a little more time, then the melt film thickness will increase such that the surface tension will get very small compared to the forces which we can apply by the gas jet, and then the melt will be sent down this cutting curve. It will slide down the cutting curve and the melt will be expulged. However, this happens in a periodic process, because as soon as we take away a certain portion of melt, the melt film thickness is practically zero, or so small that again the surface tension wins. And then we need to allow again a little more time so that again one of these drops forms and we get the formation of a melt drop, which then has enough mass and not enough surface tension to stay there, but it will be accelerated down the curve. This process, this periodic nature of the cutting process can be observed very simply in a very practical example. If you think of rain drops at a window, you will see that on top of the window there will just be the little drops and they will stick there as drops. But as soon as you have more drops coming to the window at lower parts of the window, you will see that then gravity in this case exceeds the surface tension of the drops and the drops will start to run down the window. So that is exactly the same process here, just that the gravity in the water analogy here in the laser cutting is the accelerating gas jet which pushes out the melt film. Coming back to our video, now I show it again, and now you understand better this periodic formation of the melt and the drops, so to say, and you can see that very nicely in the changing thickness of the melt. And as a consequence, this periodic modulation of the melt flow leads to these striations. So it is very systematic and not understood yet how we can prevent the process from this periodic oscillation. In reality, it's even more complex if you look at this next video. As you can see, the resulting striations now get even more complicated, and the reason for that is that the melt flow in reality is not only vertically, but it also has horizontal components around the laser beam itself, so radial components which superimpose with the vertical components, so we get a mix of these forces which result in, as we call it, striations of first and second kind. And that's again what you see very nicely in this real cut up here. Here's the first order striations and here are the striations of the second kind. As a matter of fact, there are also striations of a third kind. In order to make these effects visible, we designed a process which we called trim cut. So what we do is we take a cutting edge and we just cut and trim the edge of that piece of metal. On the other side, where actually there's no workpiece, we place a piece of glass through which we of course can look and observe the process with a camera. In doing so, we get the simulation of a cutting curve quite close to reality, and in parallel have the ability to look into the cutting curve itself. As a result, we now can look at CO2 laser cutting and at neodymium YAG laser 1 micrometer laser cutting with solid state lasers. And to explain the motivation right here, of course, if we work with a 10 micron laser, the principal speed is limited by the focusability of the laser. This is also, of course, true for the 1 micron laser. However, as you may remember or know, the 1 micron radiation can be focused at a comparable beam quality a factor of 10 better to the order of the wavelengths. So in principle, at comparable power, we will have a 10-fold smaller cutting curve using 1 micron lasers compared to CO2 lasers. And that results in, theoretically, at the limit, a 10 times higher cutting speed. Now, in reality, we cannot reduce the cutting curve widths as low. There are melt reasons why we cannot go below certain dimensions, but a factor of 3 is definitely feasible. So with a 1 kilowatt, 1 micron laser, we can cut 3 times faster compared to a 1 kilowatt CO2 laser. However, the downside is that the quality of such cuts are different. You see here summarized the challenges that we face in this context. And if we now look in this trim cut technology to the two different natures of the cuts, what we observe in using CO2 lasers is a very stable and very nice continuous melt flow. Actually, what you see here is the molten glass, so you just ignore this. This is just, so to say, the other side of the cut, which is not of interest for us. The metal cut itself is very, very stable, as you can see here in this slow motion video for a CO2 laser cut with 10 microns wavelengths. Now, if we do the very same thing with the very same parameters with a neodymium YAG laser, we observe this. And what we see here is like a firework in the cutting curve. There's no continuous melt flow. It is a continuously changing, locally and timely changing process characteristic like a firework. So that is the reason why the cutting quality with 1 micron laser radiation is still much, much worse compared to CO2 lasers. A reason and first explanations for that are the angle of incidence and the absorption characteristics due to the Brewster effect ultimately, and the second one is diffraction properties. 1 micron radiation forms shadows. If you have melt noses, then the radiation will not be bent, so to say, around these noses and homogenize the heat input, but the opposite will take place. The melt nose will evaporate, it will explode, and it will shadow the other parts in the cut, which leads to very high and very low temperatures in the cut and thus not homogeneous conditions. A theoretical analysis of this process is shown in the next video. In this movie here you see again the formation of the systematic periodic formation of these melt film characteristics, and then you can see the corresponding noses, I said, these drops that form and are accelerated down the cutting curve, and as a consequence we get high temperature and low temperature zones and thus inhomogeneity in the cutting curve. And this is what we need to come over in the future developments in 1 micron laser cutting. Coming to oxygen cutting, it is actually the same thing as fusion cutting. However, now we don't use inert gases, we now use oxygen. And as you may know, if we use oxygen and iron, we get oxidation, and this is an exothermic reaction, so we get higher cutting speeds, lower gas consumption. The disadvantages are we get oxidation of the cutting edges, and we have the risk of burning the material. As I said, the most useful advantage is the extra energy that we get from the gas jet. If you look at the net power which is used for cutting and subtract the losses, you can say about 50% of the total line energy provided comes from the reaction energy from the chemical reaction. So that is a significant booster for the cutting process. We need, if you want to put it that way, half of the laser power, or we can achieve double the speed in using oxygen. Some examples in this picture here, you see typical oxygen cut examples. The cutting quality is rather good. It's rather good. However, what is maybe even more important is the rectangularity of the cuts compared to other plasma or thermal cutting processes. You see that in all the pictures that this geometric precision is really one of the big advantages of laser cutting. Further examples in micro cutting, very small structures here, or in medium-sized applications, several thousands of such systems are used every year in new processes for making parts like this 24/7. As an outlook, the cutting is of course a still very important process, but it also can be combined with other processes in a single machine, in a single system. So we talk about integrated cutting and welding or hybrid laser production systems for specific applications. In this case here, cutting and welding is used for production of non-linear tailor-welded blanks. A tailor-welded blank is a blank consisting of two thicknesses or even two materials. And if we want to have a transition area which is not a straight line, then we can cut it individually, and with the same data we cut the other part, so we have very high repeatability. And then in the next step we put the two parts together and weld it with the same control data. Ultimately, additional functionalities can be brought into these sheets, like you see here some elliptical cuts, which of course now have a 100% precision repeatability, because all the distortion of the welding takes place before we bring in the cuts of these shapes. So laser cutting, as said, is the most used laser application today, and it probably will remain very much used also in the future. The question is which sources will be introduced. Today we talk about a transition from CO2 lasers to YAG lasers with the advantage of higher cutting speeds. Still comparable quality up to 4 millimeter of material thickness. Beyond 4 millimeters, the quality still is so low that CO2 lasers are used more intensively. The future will apply diode lasers. There are first applications of diode lasers for cutting, and in low gauges it is applied already, and it's just a matter of time and the quality of the diode lasers until they will also be used in high speed, high gauge laser cutting.